In part 2, I will speak about the discrepancy of stratified samples from partitions of the unit cube. As already mentioned, this is joint work with Markus Kiedelen from Aarhus, and the preprint can be found on arXiv. So we are now in the setting of so-called randomized quasi-Monte Carlo sampling, which is a popular method to randomize deterministic point sets. So usually in randomized quasi-Monte Carlo, you take a deterministic point set, a deterministic quasi-Monte Carlo point set as an input, and you use a certain randomization technique, for example, a random shift or a digital shift, to generate a new point set, which then can be shown to improve upon Monte Carlo samples, while you still enjoy the advantages of being random in theoretical analysis. So you start from a deterministic point set, you apply some random shift to it, and you then look at average properties over all the shifts you apply. The starting point for our work is a classical and very basic random quasi-Monte Carlo technique, which was already mentioned in a paper by Haber in 1966. So it's the so-called jittered sampling. So what you're doing here is you arrange points on a regular grid, as you can see here on the left, and then you identify each point with a grid cell, and you just randomly move the point in its grid cell. So instead of taking a grid point, you identify the point with the little cube, and then you move it freely and randomly around. So you get an arrangement, as you can see in the middle here. Every point is a random point in its own square. And you can compare this to a set of uniform samples on the right. And as I have mentioned in part 1, in a complete uniform sample, you always have this clustering, which you do not get if you use this jittered sampling. So this is the main advantage of this approach, that you avoid this clustering. And we will take a more systematic look at jittered sampling, and in particular, we will extend it to arbitrary partitions of the d-dimensional unit cube. So we consider what we call stratified sampling, where we partition the d-dimensional unit cube into n subsets, and the ith point of our point set is then uniformly chosen in the ith set of the partition and completely independent of the other points. And as a ground model for comparison, we consider a normal Monte Carlo sample, as you have seen on the picture before. So we denote Monte Carlo samples always with a capital P and capital N. So the N denotes just the number of points. So to be more concrete, well, let's pick a dimension. Let's say D is greater or equal than 2. And then we consider a partition, capital omega, of the unit cube into n Lebesgue measurable sets, such that the union of these sets gives you back the unit interval, and the sets do not overlap. So the intersection of any two sets is a Lebesgue null set. And then any such partition gives rise to an n-element stratified sample. We denote this always with a capital P and an omega here as a subscript. And since there is one point in each set of the partition, this is an n-element point set. Just as a little side remark, we discussed this in our preprint at some length. So there are alternative ways of defining point sets via partition, and one of them is the so-called Kakutani splitting procedure. So first of all, there is an obvious difference here because this splitting procedure is a one-dimensional method, whereas we work in more general dimension. However, this is not the main difference I would like to point out. The main difference here is that this splitting procedure that appeared in the literature before is a nested sequence of partition, whereas in our case, partitions or partitions for different number of points do not need to be nested. So this is just a little side remark, and for details we refer you to our preprint. So why are we interested in such partitions and sequences of partitions? So first of all, it was shown that the asymptotic order of the star discrepancy of a point set obtained from jittered sampling is better than the order you get for a random point set. So remember, for a random point set, you have n to the power of -1/2, whereas here we gain a little bit if we apply jittered sampling. And so the question is, well, jittered sampling only works if you have a square number of points. So if you have a number of points that you can nicely arrange in a square. However, we would like to have a construction that works for arbitrary n. And this is one of the motivations why we would like to look into general partitions. So the first question that comes up in this context is, in which sense are sequences of stratified sample point sets actually uniformly distributed as the number n increases? And what is the connection to similar notions of partitions in the literature? So this is what I briefly mentioned before. The second question is, does stratified sampling always give you a smaller mean discrepancy than Monte Carlo sampling? So in the case of jittered sampling, you get a smaller expected discrepancy. Is this always true for any kind of partition you choose? Also, is there some kind of best partition for a given n? And can we find a simple family of partitions that give reasonable results for all n, and not just for square numbers as in the case of jittered sampling? And finally, also, can we actually do better than jittered sampling, or is jittered sampling already the best, at least for square numbers? So these are the kind of questions we were interested in, and in the following I will present some of our results. So first of all, there is this notion of a triangular array. So imagine we do not only have one partition, but we indeed have sequence of partition. So you can imagine to arrange them in a little triangle. You write in the first row the first partition. In the second row, you write the partition into 2 sets. In the third row, you write the partition into 3 sets. And then you can, in each row, you can get a point set, which we denote here by P with subscript omega n. So each row, each partition into n sets gives you a point set, an n element point set. And this arrangement into a triangle is what is called a triangular array. And we can, in a straightforward manner, define what it means to be uniformly distributed for a triangular array. So let's start with a triangular array. So this is just a sequence of finite point sets. Then we say this triangular array is uniformly distributed if for every subcube of the d-dimensional unit cube, we have this limit relation. So the number of points of the intersection of the point set with the interval divided by m should converge to the volume of the box we are looking at. So this is exactly analogous to the definition I have shown you in part 1. The only difference here is that as we move along, so as we increase the n, point sets can change. So if you are just working with an infinite sequence, you can also write this infinite sequence as a triangular array. The only difference is that if you go from row n to row n plus 1, you carry over the first n points and you add your new point. This gives you a perfectly valid triangular array. However, this notion that we have here is a bit more flexible because it actually allows rows to be different and still gives you this asymptotic notion of uniform distribution. And then we have a characterization of the uniform of uniformly distributed triangular arrays. So we have this little limit relation here. And as a side remark, I just would like to add that the notion of triangular arrays and uniform distribution of triangular arrays is of course not new. So I know at least of one paper from the 70s of Percy Diaconis who also considered them, and I suspect one can go even further back in the literature. But if any of you actually knows where this notion originated, I would be very grateful if you can tell me. So far, my research only took me back to the 70s, but I think there must be older papers considering this. Okay, but as a remark, so in particular, if we have an infinite sequence of finite partitions, and we require that these partitions are equivolume, which means for n, all the n sets have the same volume, then the condition that we have in this theorem is automatically satisfied. So as a consequence, so whenever we work with an infinite sequence of equivolume partitions, then we know that they are uniformly distributed in this sense that we defined above. And now, before I start to show you some of our results, I need a final definition. So if we take the LP norm of the discrepancy function, then we arrive at the notion of the LT discrepancy. So remember, the discrepancy function just was the difference between the fraction of points that lie in a certain box minus the volume of the box. And if we now integrate this function over the unit cube, we get the notion of the LP discrepancy. So in particular, if P equals 2, we have the L2 discrepancy, which was already considered in Roth's theorem, and for which we have the optimal order lower bound and upper bound for the discrepancy. Now, to address the first question, well, certainly, if you allow any type of partition, then a stratified sample need not be better than a Monte Carlo sample. And you can construct very simple examples showing that. So you can start with a partition of n set of the unit square, where n minus 1 sets are all concentrated in the right upper corner of your square. And then it's a simple calculation, which we do in our preprint, that the expected discrepancy of this kind of partition is worse than what you would expect for a set of random points. But note that in this case, the n minus 1 sets are all squeezed into a tiny fraction of space. So asymptotically, as n gets larger, these sets and the volume of these sets get smaller and smaller. So this is kind of an not the kind of partition one would typically choose, but it just illustrates that, well, you can choose partitions that actually give you results that are worse than for random points. However, it turns out that if you restrict yourself to equivolume partitions, and you don't really need any other assumption, so if you restrict yourself to equivolume partitions, then in a joint work with Stefan Steinerberger, we derived what we call the partition principle, and this idea also appears on other places in the literature. And so this partition principle says that if you choose an equivolume partition, you will not do worse than you would do with just n random points. So you can only improve the expected discrepancy. And the first interesting result is that we could strengthen this in two directions. So first of all, we could replace the smaller equal that Steinerberger and I had in our results by a strict smaller, and we could extend the result from the L2 discrepancy to arbitrary LP discrepancy. So for any equivolume partition into n greater or equal than 2 sets, we have that the expected discrepancy of the stratified sample, the expected LP discrepancy, is strictly smaller than the expected LP discrepancy of a set of random points. This is what we call the strong partition principle. And the second question we were interested in was whether there is such a thing as a best partition. So whether we can define a partition such that the expected discrepancy of the point sets we get from these partitions are smallest possible. And the way we approached this question is that we were thinking, well, we need to define a class of partitions. We need to show this is compact. We need to show that the expected discrepancy is a compact function on a compact set. And in that way, we would derive the existence of a minimum. And so it turns out that a continuous function on a compact set. So, and the way we approached this was to look at sets of positive reach. So we start with a partition into n sets of positive reach. And to be of positive reach is that every point x that has a distance of r or less from the set has a unique closest point to x. So the left-hand picture here gives you an example of a set that is not of positive reach. So you have a sharp corner here, and when you approach this sharp corner, you will not have an r greater 0 such that x has a unique closest point here. So there is never such an r here, whereas for convex sets, or for more generally for sets with a smooth boundary, you always find such a unique closest point. So the right-hand side would be a set of positive reach, whereas the left-hand set is not of positive reach. And in general, this is a very large class of sets and of partitions. So what we could show for them is that if you consider the set of equivolume partitions into n sets of reach at least r, into n sets of positive reach, then there indeed exists at least one partition that minimizes the mean LP discrepancy. Of course, this is an existence result, so I cannot give you this partition, but at least we know there is a minimum here. And since sets of positive reach are a very large class of partitions, we also tried to narrow it down a little. So we have a similar result for equivolume partitions into n convex sets. And this is interesting because if you consider partitions into convex sets of the unit cube, then this is basically a hyperplane arrangement. So you can only achieve this by cuts with hyperplanes. And in that way, a convex partition can always be parameterized because, I mean, it's maybe very complicated, but in principle, this is computationally feasible. You can somehow parameterize convex partitions. And therefore, it is interesting that we also have this kind of result. So among all equivolume partitions into convex sets, again, there exists a best partition. So to illustrate this, we looked at the easiest examples. So we partitioned the unit square into two sets, into two convex sets. So one can parameterize the space of all convex partitions into two sets by fixing the center point and then letting all these all the cutting hyperplanes rotate. So you get all convex partitions into two equivolume sets by just rotating this line around the midpoint. And it turns out that the minimal partition in this family is actually the partition that I have shown here. So if you just take the anti-diagonal, then this gives you the lowest expected discrepancy, and the value here is 0.05. So we solved this problem for the easiest case of d equal 2 into two sets. And now things start to get interesting, because so far we only considered equivolume partitions, but we were then thinking, well, what happens if we start from the anti-diagonal and if we just move this line a little bit? So if we just move it along the diagonal, if we consider parallel lines to the anti-diagonal, and it turns out that if we actually relax this volume constraint, we can win a little bit. So the partition I have shown you here is having a smaller expected discrepancy. And I find this an interesting observation. I mean, there are several results that indicate that there is an asymmetry, in particular if you consider star discrepancy type discrepancies, because it's always very much focused on the origin here. And so from that point of view, it's actually not surprising that you can win something, but it's just interesting to have concrete examples here. So to sum up the second part, another question of us was to derive infinite families that give you a nice expected discrepancy for arbitrary n. So we experimented with several families. So for example, we can consider a vertical strip partition. Here you just have n equispaced lines that partition your unit interval, and it can be shown that this arrangement improves random points as it should by the strong partition principle, but you can also imagine that this is not an ideal situation, because you can still have very bad arrangements of points. Imagine all your random points somehow lie in the upper part of your unit square. What turned out to be a much better strategy is to actually arrange points in this anti-diagonal manner. So if we look at the diagonal and if we pick points along the diagonal and then we just construct lines that are orthogonal to the diagonal, then it turns out this improves the expected discrepancy of a classical Monte Carlo set by a constant factor, and by a constant factor of 2. So this would be a family of partitions that work very well, that are still easy to construct, but that guarantee you a gain over a uniform point set. So here, to sum up, there are some numerical results. The first column, this is the expected discrepancy of a set of n random points, and here n goes from 50 to 450. Then I can show you the value for the vertical strip partition. Here we can actually calculate the expected discrepancy, and you can compare. This value is always considerably smaller. Now if we turn to the partition into these parallel lines orthogonal to the diagonal, then we can calculate the expected discrepancy empirically using Warnak's formula and about 500 samples each. And we can see here that the expected discrepancy is always about a factor 2 smaller than the expected discrepancy of a uniform random point set. And just for comparison, the expected discrepancy of a set of a cheated point set is usually much smaller, and this is due to the fact that here we have actually a better asymptotic order. So the downside of our general construction is that the asymptotic order is still the same as the order of a Monte Carlo set. It's just a constant factor better. Whereas for jittered sampling, we have actually a better asymptotic order, which makes the discrepancy go down quite quickly. But the downside is it only works for square numbers. And with this, I would like to close the second part and just give you some references and pointers to the literature.